Welcome back to Math 215, Mathematical Statistics. Today we'll be discussing Part 2 of hypothesis testing. In particular, we'll be looking at tests concerning variances and tests concerning proportions. These are sections 13.4 and 13.5 from your textbook. It's worth noting that tests of variances are important from a practical standpoint. For example, manufacturers who need to meet rigid specifications will have to perform such a test on the variability of their products. Likewise, drug manufacturers may be interested in the potency of their medication and they need to know the variation in that potency. So the first test we'll consider here is the test for the variance when we're looking at a random sample drawn from a normal population. And here in this case we'll say that that normal population has variance sigma squared. Our null hypothesis will state that sigma squared is equal to sigma naught squared for some number, versus, again, we have three options for the alternative. The first would be the two-tailed alternative, which would say that the variance is not equal to sigma naught squared. The left-tailed test will say that the variance is less than sigma naught squared, and the right-tailed alternative would say that sigma squared is greater than sigma naught squared. And our test statistic will be our old friend, the chi-square score, which we compute by doing 1 less than the sample size times the sample variance, and we'll divide that by the hypothesized value of the variance that we get from the null hypothesis. When we're looking at rejection regions for this particular test, our left-tailed test is going to be constructed by looking at the chi-square distribution with n-1 degrees of freedom. In particular, we'll chop off an area in the left tail equal to alpha, and that means that we're looking for a critical value where the area to the right of that critical value is 1 minus alpha. In other words, our rejection region for the left-tailed test is going to consist of chi-square scores where the chi-square value is less than or equal to a critical value where the area to the right of that critical value is 1 minus alpha under the distribution that has n-1 degrees of freedom. Similarly, when we're looking at the right-tailed test, we're going to chop off an area in the right tail equal to alpha. So that means that we're going to be looking for a critical value where the area to the right is alpha, so we call that chi-square sub alpha. In other words, the rejection region for the right-tailed test will consist of chi-square values that are greater than or equal to chi-square sub alpha under the distribution with n-1 degrees of freedom. And similarly, when we go to our two-tailed test, we'll proceed as we've done before. We're going to have an area of 1 minus alpha in the center. We're going to take the remaining area of alpha, chop it into two tails, and put half of it in the left tail and half of it in the right tail. What that means for us is that the rejection region for a two-tailed alternative hypothesis would say that we're looking for chi-square scores where they're either less than or equal to the chi-square score with an area of 1 minus alpha over 2 to the right, or they have to be greater than or equal to the chi-square critical value with an area of alpha over 2 to the right. Let's look at an example. Suppose we have a company that produces machine engine parts that are supposed to have a diameter variance no larger than 0.0002, and these diameters are measured in inches. And suppose we have a random sample of 10 parts that yield a sample variance of 0.0003, and we want to test at the 5% significance level to determine if the diameter variance exceeds 0.0002. So to start, in order to perform this chi-square procedure for our test of variance, we'll have to assume that the measured diameters are normally distributed. Then we can define our null hypothesis to be that the variance is equal to the 0.0002, which is what the company requires. And we're going to compare that to their cutoff value, which is where they start having problems with their production line. The question is the variance greater than 0.0002? So the critical region then, remember, is going to be constructed by taking a chi-square distribution and chopping off an area in the right tail equal to alpha. So we're looking for the chi-square score that has an area in the right tail of alpha equal to 0.05 with 9 degrees of freedom. If we look that up on a chi-square table, we'll see that the chi-square score for an area of 0.05 with 9 degrees of freedom is 16.919. Next, we'll compute our test statistic. We'll do 1 less than the sample size, which is 9, multiply it by our sample variance, which is 0.0003, and divide by the value of the variance given in the null hypothesis, which is 0.0002. If we do, we'll get a test statistic of 13.5. This value is not in the rejection region, so we're going to fail to reject the null hypothesis, which means at this time there's insufficient evidence to suggest that the diameter variance exceeds 0.0002 at the 5% significance level. Next, we'll move on to a test for the equality of variances, and this is going to parallel the work that we did when we were constructing confidence intervals for sigma 1 squared over sigma 2 squared. You might recall that we were already using that confidence interval to make statements about whether or not it was reasonable to assume that variances were equal, and we used that in particular so that we could make statements later about whether or not it was legitimate to perform a pooled t-test when looking at the difference between two means when we're assuming variances are equal. So for this test, we're going to assume that we have independent random samples of size m1 and n2, and they'll be drawn from normal populations with variances given by sigma 1 squared and sigma 2 squared. The null hypothesis will state that sigma 1 squared is equal to sigma 2 squared, in other words, that the variances are equal. Versus, again, we typically have three alternatives, either that the variances are not equal or that one is less than the other. When we go to compute the test statistic for this particular scenario, we're going to have to pay attention to how our populations are labeled. So if it turns out that our sample variance for the first population is greater than or equal to that of the second population, then our F statistic, which is our test statistic, will be S1 squared over S2 squared. If it so happens that our populations are labeled in such a way that the sample variance from the first population is less than the sample variance for the second population, then our test statistic will just be the reciprocal of what it was in the previous case. We'll look at S2 squared over S1 squared. And so because we have to consider that situation, some interesting things to consider when we're looking at rejection regions. In particular, if we're looking at what we would typically consider to be our right-tailed alternative hypothesis, then in this case, we're going to reject the null hypothesis if our test statistic, S1 squared over S2 squared, is greater than the F critical value with an area of alpha in the right tail with n1 minus 1 numerator degrees of freedom and n2 minus 2 denominator degrees of freedom. If it so happens that we're working with a left-tailed test, and in this case, that's probably going to happen if we notice that the S1 squared is less than the S2 squared, then remember our test statistic is the S2 squared over S1 squared, and we're going to reject the null hypothesis if that test statistic is greater than the critical score given by the F distribution with an area of alpha to the right. But in this case, the numerator degrees of freedom are n2 minus 1, and the denominator degrees of freedom are n1 minus 1. In the case that we have a two-tailed test, we have to decide which scenario we're working with. Is the sample variance from the first population greater than or equal to that for the sample variance for the second? If so, then we're going to reject the null hypothesis if our test statistic S1 squared over S2 squared is greater than the critical value for the F distribution where we have an area of alpha over 2 to the right, with n1 minus 1 numerator degrees of freedom and n2 minus 1 denominator degrees of freedom. Otherwise, if we're working with a situation with the sample variance from the first group is less than the sample variance from the second sample, then we're going to reject the null hypothesis if our test statistic of S2 squared over S1 squared is greater than or equal to the critical value for an F distribution with an area of alpha over 2 to the right, where our numerator degrees of freedom is given by n2 minus 1 and our denominator degrees of freedom are given by n1 minus 1. It's important to notice here that when we're looking at all of these rejection regions, they all give the impression that we're working with an F distribution with a right-tailed type of rejection region, and what differs is what we have in terms of our choice for our numerator or our denominator degrees of freedom. That being said, this seems like an awful lot of stuff to sort of memorize or keep track of, but you might notice that if we're careful in the way we label population 1 versus population 2, if we always pick population 1 so that it's the scenario where when we're comparing our sample values that the S1 squared, say, is greater than or equal to the S2 squared, then what we end up with for the right-tailed test or for the first option when we're working with the two-tailed test, gives us the same test statistic and the same kind of structure for our rejection region with our numerator and denominator degrees of freedom. So if you're careful about the way you label population 1 versus population 2 when you perform this test, then you might have fewer details to worry about when thinking about, given your alternative, what does your rejection region look like. It's entirely up to you which way you want to go on this. Let's look at an example. We're going to compare the variation in diameters of machine parts produced by two companies. And before I get very far into this, I should make a comment that there is a typo on this slide. So this first value, 0.0003, should be our S1 squared, and the second value, 0.0001, should be our S2 squared. So here, company A, this is the same company we had in the previous example where we had a sample size of 10 and a sample variance of 0.0003. And we're going to look at competitor company B, where we look at a sample of 20 produced machine engine parts by them and the associated sample variance of 0.0001. Now let's test at the 5% significance level to determine if the data provides sufficient evidence to indicate a smaller variation in diameters for company B. And so we'll notice here that S1 squared is greater than or equal to S2 squared. In order to perform a test here, we're going to have to assume we're working with independent random samples from normal populations. And since we notice that our S1 squared is greater than or equal to our S2 squared, and we're trying to determine if the variation in diameters for company B is smaller than that of company A, it seems reasonable that our null hypothesis would say that the variances are equal, but our alternative would say that sigma 1 squared is greater than sigma 2 squared. In this case, that gives us a right-tailed alternative. And if we're going to construct our critical region is going to be the set of values where S1 squared over S2 squared is greater than or equal to the F score with an area of 0.05 in the right tail with 9 numerator and 19 denominator degrees of freedom. If we look that up in the F table, we'll see that the value for our critical score is 2.42. Then we'll go to compute our test statistic. This is S1 squared over S2 squared. So we take the ratio of those two variances from our samples and we get 3. We see that this is in the critical region, and therefore that means we're going to reject the null hypothesis. So that tells us that based upon this data at the 5% significance level, there is sufficient evidence to suggest a smaller variation in diameters for the machine engine parts produced by company B.